So let's start the next section of chemical bonding. So let's talk about geometry of molecules. So it is a relative arrangement of atoms in molecule. For example, for LiF2, we can say that it has a linear geometry, and for water, it is at an angle. So you can see that this straight line and this angle, so this is all concerns about the geometry of a molecule. So it's a relative arrangement of atoms in a molecule. So how we can find the geometry of the molecules? So one is VSEPR theory for that. We also call it as valence shell. It's a short of valence shell electron pair repulsion theory. So this theory's postulates are: the geometry of a molecule depends upon number of valence shell electron pairs, either bonding or non-bonding. For example, in case of water, there will be one pair here, and there will be one pair on the outside and one more pair on the outside. So it depends on the number of valence shell electron pairs. So in this case, the number of valence shell electron pairs are 4. 3 pairs, these pairs repel each other, therefore try to stay as far as possible. Relative repulsion. So lone pair, so these are the lone pairs. So lone pair, they repel more than lone pair bond pair, that is this case, and they have more repulsion than bond pair, which is this. So this has the maximum repulsion, this has next, and then this has the least repulsion, bond pair. So let's take some examples. So molecules with bond pairs only. So one is BeF2. So these two will try to repel as far as possible. So angle between them will be 180 degree. BF3, it has total of 3 pairs. So again, they will try to go as far as possible to each other. So angle between them will be 120 degree. Here is a tetrahedral structure of CH4. There the angle is 109.5 degree. So between each of the two bonds, the angle is 109.5 degree. Again, this means this is coming out of the plane, and this means it's going inside the plane. So it's a 3D structure. These two are, this is planar structure, this is a linear structure, and this is a 3D structure. So 1D, 2D, 3D. Molecules with both bond pair and lone pair. In case of NH3, it has a lone pair here and 3 bond pairs. So here you can see that the repulsion between lone pair and bond pair is more than repulsion between bond pair and bond pair. So here repulsion is less, so this angle is 109.5 degree. Here the repulsion is much more, therefore this angle is becomes shorter. So here it was 109.5 and here it has become 107 degree. Second case is your water molecule. It has 2 lone pairs. So the repulsion is even more among here and here. So this angle is further down to 104.5 degree. So you can see that it's decreasing because bond pair repulses least and lone pair repulses most. So both of these are distorted tetrahedral geometry. This is a perfect tetrahedral. Quantum theory of covalent bond. So here we will introduce the concept of orbitals. I mean, we already have studied about orbitals, but how we'll utilize this concept of orbitals in bond formation, covalent bond formation, that we'll see here. So its first is valence bond theory. So let's just read about the postulates of this theory. So it says that atomic bond forms when orbitals. So what are orbitals? We have already studied. They are like s, p, d, f, like that. So when orbitals possessing opposite spin overlap. So during bond formation, spins of 2 electrons get neutralized. So both of these orbitals which are forming in an atomic bond, the electrons should have opposite spins. So electrons should possess opposite signs. and when the bond is formed, the spin is neutralized. If spins are parallel, that means they are in the same direction, then repulsion takes place and no bond is formed. So this is just a theory, just we'll go through it quickly, and when we'll do some examples, then it will make more sense. Strength of this bond depends on extent of overlapping. And how we decide that extent of overlapping is from this something called overlap integral, which is S is equal to integral of psi A into psi B. We studied before in our atomic structure that this psi A and psi B are the electron wave functions. So just leave it to that. This equation is not important, but this is just to give you an idea that it depends on both of the wave functions of both the electrons. So if this integral is positive, that means that there is more electron density between nucleus and covalent bond forms. So if these are the two nuclei, and if this integral is positive, that means electron density is more between the two nucleuses. So this attraction and this attraction between the nucleus and the electron cloud will keep the whole bond strong. And if it is negative, S is negative, that means the less electron density between nuclei. So that means there is very rarely any electron cloud between the nuclei. Therefore, the nuclei itself will repel each other and no bond is formed. Third, only atomic orbitals of unpaired electrons overlap to form bonds. So this we already know. So one, and not just they should be unpaired, they should be of opposite spins. If an atom possesses more than one unpaired orbital, then multiple bonds may form. That means, like, let's say it has an atom has S and P like that, and it has two orbitals, one of the p orbital and one of the s orbital. Both have one unpaired electron each, so multiple bonds can form. So here two bonds can form. Combining atoms retain their identity. Pretty straightforward. If carbon and four hydrogens are combining together, carbon atom will remain carbon atom and hydrogen will remain hydrogen atom. It's not that some hybrid element will get formed or anything like that. No. So it's just a basic postulate. Bond formed lies in the direction of maximum overlap. So let's take an example of there is one hydrogen which has an s orbital, and there is p orbital of, let's say, oxygen, and they overlap like this. So this postulate means that the direction of the bond is along the direction of maximum overlap. So maximum overlap is this line here in the center of it. So let's say this is, so where is the maximum overlap? You can see it is here in the center. So this is the direction of bond formation, in the direction of maximum overlap. The covalent bond is therefore directional in nature. So this bond, we can say its direction is along this line. Axial overlap between orbitals of same energy forms a stronger bond. So let's understand the difference between axial overlap and perpendicular overlap. So this overlap is axial because the nuclei of both, when you combine the nuclei of both the atoms, the bond is also in the along of that axis. But sometimes the p orbitals, they overlap like this. So here the bond, the axis is this, but the overlap itself is not along the axis. Therefore, this is not that strong as this one. S orbital being symmetrical shows no directional preference. So this is a s orbital, so it can attract any other orbital from any other direction. So for example, another s orbital can combine it from here like this or like this, can combine from any side because this is symmetrical. But a p orbital will have a directional preference which is along axis. So it will prefer to form a bond here and it will not form a bond like this because it has a preference along axial direction. So that's what this means. So let's talk about some of the overlappings. S overlapping. So these are two s orbitals, they will overlap like this. Sp overlapping. So S, and let's say this is Px. So there will be two more dumbbells which will represent Py and Pz. But we are talking about just Px now. So their overlap will be like this. So again, it's preferably along the axis. PP overlapping. So it can be heads-on or axial or sideways or lateral. So axial is when the bond is formed along the axis. Sideways is when the p orbitals are perpendicular to their axis. So it will be formed like this. So the electron density will be like here and here of the combined orbital. We'll learn about this later in detail in a bit. But for now, you can just think that they overlap like this. Sigma bond and pi bond. So here in these two cases, when the bond is along the axis, they are called as sigma bonds. And when they are perpendicular, in this case, so these are the axis of the orbitals and actual bond is perpendicular to the axis of orbitals. So this bond is called a pi bond. Needless to say, sigma bond is stronger than pi bond. It's one of the postulates that it should be there. Yeah, here axial overlap between orbitals of same energy forms a stronger bond. So till now we were talking about atomic orbitals and their overlap, and in the diagrams which we drew, we retained the shape of the orbitals, but in reality the original orbitals actually lose their shapes and they eventually form something which is called molecular orbital. So we studied that this will be an S and this will be a P, so it will eventually look something like this and the sharing will be along this, but this does not happen. So S and P, they will combine to form a molecular orbital, and we'll talk about that molecular orbital, how it looks like and how it behaves. So let's do some theory and then we'll see some examples. When atoms approach each other, their atomic orbitals lose their identity and mutually overlap to form new orbitals. These new orbitals are called molecular orbitals. Orbitals are polycentric. These molecular orbitals are polycentric. That is, they surround the nuclei of combining atoms and electrons move over the whole nuclei system. Molecular orbitals are formed. So, okay, this means that it's not that this electron will be limited, its electron will be limited to be shared along its border, and same with this electron. This something called molecular orbital forms, and when the two nucleuses are like this, these electrons, shared electrons, will actually move around both the nucleuses. So their orbitals are polycentric. Molecular orbitals are formed only by those orbitals with comparable energy and possess proper orientation. So just like we studied before, that this orientation is not proper, so it will not happen. So it's an extension of your valence bond theory. So don't think that everything in valence bond theory is wrong. So this molecular orbital theory is an extension of that. So until your orientation is correct and the energy levels are comparable, the bond will not be formed. A molecular orbital can hold maximum 2 electrons. Molecular orbitals get filled with same rules as applied for filling of atomic orbitals, which is Pauli's exclusion principle, Hund's rule, and Aufbau principle. So all three of them combined, if you remember that chart where this cat fills first, then this, and S, SP, SPD. So this filling of the orbitals in this order, and there should be a maximum of 2 electrons in each orbital. And first the whole, for example, in the case of p orbital, all three will be singly filled, only then the pairing will start. So all these rules combinedly are these three rules. So the electrons, the molecular orbitals, they get filled with the same rules. So we have already studied those rules before, but later we will summarize these rules again just in case. So formation of molecular orbitals. So let's understand a bit in detail how they are formed. So it's a quantum theory, so it's basically theoretical. There's not much mathematics involved, but just to understand it a little bit. So you can think of an atomic orbital as an electron wave function. So this is a kind of a wave of that electron. It will have a crest and a trough. So this represents an electron wave, and this is one of the electron atomic orbitals. So for bond formation we need two atomic orbitals. So when two such atomic orbitals come close, then there are two possibilities. First is their electron waves reinforce each other. So if the first wave is like this and second wave is also like this, then they will reinforce each other and an attractive molecular orbital of low energy is formed, and it is called as bonding molecular orbital. When electron waves oppose each other, so one is like this and other is like this, so both are opposite to each other, a repulsive molecular orbital of high energy is formed called anti-bonding molecular orbital. And we know that low energy is more stable. That's why this is attractive. And when the energy is high, it is unstable. So it is a repulsive molecular orbital. So this molecular orbital is called anti-bonding molecular orbital. So whenever, again to summarize, whenever a molecular orbital is formed, it will have a bonding molecular orbital and anti-bonding molecular orbital. So there are some notes corresponding to atomic orbitals s, p, d, etc. The molecular orbitals are represented by sigma, pi, delta, etc. That is to say that if two s bonds are combining together, that will be a sigma bond. So even between s and p, it will be called a sigma. Between p and p, it will be a pi. P and d, it will be a pi, like that. The anti-bonding molecular orbitals, don't worry about it if you don't understand much, it's fine. The anti-bonding molecular orbitals are represented by putting an asterisk over the symbols. The molecular orbitals are shown in an energy level diagram. So let's take an example of two atomic orbitals, 1s and 1s, which are combining to form a bond. So what we studied is when these two atomic orbitals combine, they will form one bonding orbital and one anti-bonding orbital. Bonding orbital should have less energy and more stable, and anti-bonding should have more energy. So this is the energy diagram for that 1s molecular orbital. So it's represented like this. Along the y-axis, it's the energy. So higher the something is, it has more energy. So bonding will be lower, anti-bonding will be higher. These green dots, they represent that on the left it is your atomic orbital. Right of this is also an atomic orbital, and in between these two lines is your molecular orbital. So this one, which is at lower place, it's bonding molecular orbital. So one molecular orbital can only hold 2 electrons. So it will hold both the 2 electrons of your 1s and 1s. And this anti-bonding molecular orbital will be empty because it had 1 electron, this 1s, this had one electron, and only unpaired ones can form a bond. So that means only 1 and 1 are here. Both of them will combine to form this. So both electrons will go to the bonding molecular orbital, and anti-bonding molecular orbital will be empty. Is represented by sigma 1s and asterisks. This is a simple case. We'll soon see some real examples of some real molecules and how their energy level diagrams are made. So this is the simplest of all. So we saw briefly about the wave functions and how they will merge, and depending on if they are both in sync, they will actually form a bonding orbital, molecular orbital, and if they are opposite, their natures are opposite, then it will be an anti-bonding molecular orbital. And we remember that S is equal to integral of psi A psi B, which was for the case of your atomic orbitals. So when both for a bond, covalent bond. So when S was found to be positive, that covalent bond would exist, and if it's negative, it won't. So when two electron waves are in phase, the electron density is between the two nuclei, therefore shielding the two nucleus from each other, and it is a stable one, and due to this mutual attraction, it's a low energy orbital. So let's say this is the wave function xi A and this is the wave function xi B. So if they are in phase, then we will add them. So let's add these two. So it will look something like this, right? So this electron density between A and B now is more. So you can think of this as this xi A represents your electron density or an electron wave function or something like that. So this is the nucleus of A. So you can see that near the nucleus of A, the probability of finding the electron is more, and as you go away from the nucleus of A, it decreases. Similarly for the B. So when the molecular orbital is formed, it becomes a sum of xi A and xi B. So it looks something like this, and as you can see that now the probability of finding the electron between the two nuclei is actually much more. So this is xi A plus xi B, and our probability is obviously a positive term always, so we talk about the square of that. So it will be something like this. So this is your eventual electron density. Anti-bonding molecular orbital, so when they are not in phase, so electrons are not between the nuclei, therefore nuclei repel each other, hence it is repulsive orbital of higher energy. So this is xi A and we have to subtract it, so let's draw xi B like this. So this is minus xi B. So xi A minus xi B will be something like this, and if we do a square of it, it will come something like this. So this is xi A minus xi B whole square, and if you compare these two, you can see that here the probability of finding an electron is much less. So electron stays very less, that electron pair stays very less between the nuclei, and therefore the nuclei, they will tend to repel each other. So this molecular orbital, which is the anti-bonding molecular orbital, is not as stable as this. So molecular orbital from two s orbitals. So 1s and 1s will combine to form sigma 1s and sigma 1s star, which is your anti-bonding molecular orbital. Molecular orbital from two p orbitals. See, now the electrons which go into them, that we can discuss later, but when 1s and 1s are combined, these orbitals, then it will give rise to two molecular orbitals. Molecular orbitals from two p orbitals. So depending on what kind of overlap it is, let's talk about the heads-on overlap first. So 2pz and 2pz, if this is the z-axis along this, so 2pz and 2pz will be like this. This is a head-on overlap. So your sigma, this will be a sigma bond because they are along the axis. The bond formed is along the axis of the orbital itself. So sigma 2pz, it will look like this. So this is your final molecular orbital. It will look like this. And sigma 2pz asterisk, so it will look something like this. So here also you can see that between if the nucleus are somewhere here, the probability of the electron density between the two nucleus is less. Here it is more. So this is more stable, xi A plus xi B. And when the overlap is sideways, then it looks something like this. So this is a pi bond because the axis of the orbital is perpendicular to the axis of bond. So the bonding orbital will look like this, and anti-bonding orbital looks something like this. So sigma molecular orbital is stronger than pi. So this is just a revision of what we have studied, as overlap is more due to heads-on overlap along the internuclear axis, therefore symmetrical to it. So you can see that those sigma bonds are always symmetrical to the axis. So if this is the axis, and if you rotate this sigma bond along this axis, you will find the same geometry anytime. Similarly with the S and S, or P and P, axial overlap. So in all these cases, they are symmetrical to the axis, but this is not. So if you rotate along the axis, it will not be the same geometry. Here they are in, let's say, y direction. If you rotate by 90 degree, they will be in x direction. So if there was a probability of finding an electron in y direction before, if you rotate it, it's no more. So this is not symmetrical. Molecular orbitals get filled by Reuleaux. So these are the three rules. So this is a revision of Bohr principle, which is that the molecular orbital with lower energy gets filled first. Pauli's exclusion principle, that maximum 2 electrons can be there in one molecular orbital. And Hund's rule, that electrons prefer to be unpaired in a molecular orbital. Pairing happens only when vacant orbitals of same energy are not available. So again, 1s and 1s, this can hold 2 electrons, this can hold 2 electrons, and if there is a bond which is forming, something is happening, then it will give rise to 2 molecular orbitals. One is bonding. In this case of S and S, it will be something like this, and the anti-bonding will be something like this. So this can hold 2 electrons, and this can also hold. So these 4 electrons, they'll be filled something like this. So when only there are unpaired electrons, so 1 and 1 of both the atoms, then both of them will fill into a bonding molecular orbital. So when we will do some real examples in the next part, you will get a better feel of what we are talking about here. So that will be the final lecture of chemical bonding.